Hello, and welcome. It's good to have you here in this quiet moment, wherever you are. Tonight, we're going to drift together into the world of icebergs, those silent wanderers of the polar seas, moving through cold water with a patience that seems almost impossible to imagine. They travel without hurry, without sound we can easily hear, carrying within them secrets that stretch back thousands of years. You can let your shoulders settle if you'd like. There's no rush here, no urgency in anything we'll explore together. I know you might be tired. Perhaps the day has asked much of you, or perhaps you're simply ready to let your mind wander somewhere calm and cool and vast. Either way, you're welcome here, in this space where science becomes something soft, something that asks nothing of you except to listen, and even that is optional. You might drift in and out of these words, and that's exactly as it should be. If these journeys bring you comfort, you're welcome to return anytime. There are many nights ahead, many quiet facts waiting to be discovered, and none of them are going anywhere. So let's begin gently with the first truth about icebergs and the way they move through the world. Icebergs are born from glaciers, those ancient rivers of ice that flow so slowly down mountainsides and across polar landscapes that you could watch one for your entire life and barely see it move. When a glacier reaches the ocean, something inevitable happens. The ice at its leading edge begins to feel the tug of warmer water, the rise and fall of tides, the gentle insistence of waves. Eventually, a piece breaks free. This breaking is called calving. And though it can be dramatic, with ice crashing into the sea and sending up plumes of white spray, the iceberg that results enters into a life of profound stillness. Once it floats free, once it finds its balance in the cold water, it begins a journey that might last months or even years, and most of that journey unfolds in near total silence. The silence of an iceberg is one of its most remarkable qualities. When you think of ice, you might imagine the crack of a frozen lake, the sharp sound of ice cubes splitting in a glass. But an iceberg, once it is settled into the ocean, becomes something else entirely. It drifts. It moves with the current, turning slowly, tilting slightly as its weight shifts, but all of this happens without the sounds we associate with movement. There is no engine, no wind in sails, no friction of wheels on a road. There's only the quiet displacement of water, the slow rotation of mass, the patient progression from one place to another. This silence is not emptiness. Beneath the surface, the ocean around an iceberg is alive with sound, with the clicks of marine mammals, the hum of distant ships, the creak of the iceberg's own structure as it adjusts to temperature and pressure. But from a human perspective, standing on the deck of a ship or on a distant shore, an iceberg appears to move through the world as if it exists in a separate dimension, one where time runs differently, where urgency has no meaning. The size of an iceberg can be difficult to comprehend until you're near one. We've all heard the phrase, tip of the iceberg, and it's true that only about 10 to 15% of an iceberg's mass is visible above the waterline. The rest, the vast majority, hangs below, hidden in the dark water. This happens because of density. Ice is less dense than seawater. Freshwater ice, which is what icebergs are made of, has a density of about 917 kilograms per cubic meter. Seawater, especially the cold seawater of polar regions, has a density of about 1,025 kilograms per cubic meter. This difference is just enough to allow the ice to float, but not enough to keep most of it above the surface. So an iceberg sits low in the water, most of its body submerged, only a small portion exposed to the air and light. This hidden mass gives icebergs their stability. A large iceberg can weigh millions of tons, and all that weight below the surface acts as a keel, keeping the iceberg steady as it drifts. The shape of the submerged portion can be complex, with ridges and valleys and protrusions that have been carved by the glacier's movement over land and then smoothed by the water. Sometimes an iceberg will have a long, narrow extension reaching down into the depths, and this can make the iceberg behave in unexpected ways, catching deeper currents and moving in directions that seem contrary to the wind or surface water. The color of an iceberg is another source of quiet wonder. Most icebergs appear white, and this is because of the air trapped within the ice. When snow falls on a glacier, it accumulates in layers, and as more snow falls on top, the lower layers are compressed. Air bubbles become trapped in this process, and when light enters the ice, it scatters off these bubbles, reflecting back to our eyes as white. This is the same reason snow appears white, even though water itself is clear. But not all icebergs are white. Some have bands of blue, deep and vivid, almost glowing. This blue ice forms when snow is compressed so thoroughly that most of the air is squeezed out. Without air bubbles to scatter the light, the ice absorbs the longer wavelengths of light, the reds and yellows, and reflects back the shorter wavelengths, the blues. The result is a color so pure and intense that it seems almost unnatural, as if the iceberg has captured a piece of the sky and frozen it. Occasionally, you'll see icebergs with dark streaks or bands running through them. These are layers of sediment, rocks and soil that were picked up by the glacier as it moved over land. The glacier acts like a conveyor belt, gathering material from the ground and carrying it along. And when the iceberg calves off, it takes this material with it. These dark bands tell a story of the glacier's journey, a record of the landscape it crossed, now preserved in ice and floating far from where it began. The temperature of an iceberg is remarkably consistent. The ice itself is at or very near 0 degrees Celsius, the freezing point of fresh water. Even in the coldest polar air, the surface of an iceberg won't get much colder than this, because ice has a high specific heat capacity, meaning it takes a lot of energy to change its temperature. In warmer conditions, the surface might begin to melt, but the interior remains cold, insulated by the outer layers. This consistency is part of what makes icebergs such stable travelers. They don't react quickly to changes in their environment. They absorb warmth slowly, release cold slowly, and move through temperature gradients with a kind of thermal inertia that matches their physical inertia. The movement of an iceberg is governed primarily by ocean currents. Wind can push on the exposed portion of an iceberg, and this does have an effect, but because so much of the iceberg is underwater, the currents have a much stronger influence. In the Arctic and Antarctic, there are well-established current systems that carry icebergs along predictable paths. In the North Atlantic, for example, icebergs calved from Greenland's glaciers are caught by the Labrador Current, which flows southward along the coast of Canada. These icebergs can travel remarkably far south, sometimes reaching the waters off Newfoundland, and in rare cases, even further. The journey can take months, and during that time, the iceberg is slowly melting, gradually losing mass, shrinking as it drifts into warmer waters. The speed of this drift is slow by human standards, but not insignificant. An iceberg might move at a speed of about half a kilometer per hour, though this varies greatly depending on the current, the wind, and the iceberg's shape. Over the course of a day, an iceberg might travel 10 or 12 kilometers. Over a week, it could cover 100 kilometers or more. This is not the pace of a ship or even a swimming animal, but it is steady, relentless, a kind of movement that never stops, never pauses, continuing day and night, through storms and calm, through darkness and the pale light of polar summers. There is something deeply calming about this constancy. In a world where so much demands our immediate attention, where speed is often valued above all else, an iceberg offers a different model. It moves because the ocean moves. It goes where the water takes it. There is no decision, no effort, no striving. Just drift, just the slow, inevitable progression from one place to another, shaped entirely by forces larger than itself. The shape of an iceberg changes as it melts. When an iceberg first calves from a glacier, it often has a blocky, angular shape with flat sides and sharp edges, reflecting the structure of the glacier it came from. But as it floats in the ocean, the water and air begin to work on it. The waterline, where the ice meets the sea, melts faster than the ice above or below. Waves lap against the ice, wearing it away, creating a notch that runs around the iceberg's perimeter. Meanwhile, the sun warms the exposed upper surface, causing it to melt and form pools of water. These pools can be quite beautiful, little lakes of the purest blue sitting atop the white ice. But they also contribute to the iceberg's transformation. The water in these pools absorbs more heat than the ice around them, accelerating the melting process. As the iceberg loses mass unevenly, its center of gravity shifts. An iceberg floats in equilibrium, balanced according to the distribution of its mass. When enough ice melts from one part of the iceberg, it can become unstable. The iceberg will then roll, sometimes slowly, sometimes quite suddenly, seeking a new balance point. This rolling can be dramatic if you're there to witness it, with the iceberg turning over, exposing surfaces that have been underwater, now wet and gleaming, and submerging portions that were dry. But once the roll is complete, the iceberg settles again into stillness, into that same patient drift, now in a new orientation. The lifespan of an iceberg depends on many factors: its size, the temperature of the water and air, the currents it encounters, the amount of sunlight it receives. A small iceberg, sometimes called a growler or a burgee bit, might last only a few weeks. These are the fragments, the pieces that have broken off from larger icebergs or calved as small chunks from a glacier. They sit low in the water, often difficult to see, and they melt quickly. A large iceberg, one of the massive tabular icebergs that calve from the ice shelves of Antarctica, can last for years. These are the giants, flat-topped and vast, some of them tens of kilometers across. They drift through the Southern Ocean, slowly disintegrating, breaking into smaller pieces, each of which continues its own journey until nothing remains but cold water. There's a certain poetry in the way an iceberg returns to the ocean. It begins as snow, falling on a glacier perhaps thousands of years ago. That snow is buried, compressed, transformed into ice. The ice flows slowly toward the sea. It breaks free, floats, drifts, and melts. And in melting, it becomes water again, joining the ocean, indistinguishable from the waves around it. The cycle is complete. The atoms that made up the iceberg are now part of the sea, and they will rise as vapor, form clouds, fall as rain or snow, and perhaps, in some distant future, become part of another glacier, another iceberg, another silent drift. The water that comes from a melting iceberg is fresh, not salty. This might seem obvious, since the iceberg is made of frozen fresh water, but the implications are interesting. When an iceberg melts, it releases fresh water into the ocean, and this can create a layer of less dense water around the iceberg. Fresh water is less dense than salt water, so it tends to float on top. This layer can be quite distinct, and it affects the local environment. Marine organisms that are sensitive to salinity might be attracted to or repelled by this freshwater plume. The mixing of fresh and salt water also affects the way heat is distributed in the water column, creating complex patterns of temperature and density that influence currents on a small scale. The ice in an iceberg is old. Depending on where the iceberg came from, the ice can be hundreds or even thousands of years old. When snow falls on a glacier, it is buried by subsequent snowfalls, and over time, it is compressed into ice and slowly carried along by the glacier's flow. The deeper you go into a glacier, the older the ice becomes. Some glaciers in Antarctica contain ice that is hundreds of thousands of years old, ice that fell as snow long before human civilization began. When an iceberg calves from such a glacier, it carries this ancient ice with it. Inside an iceberg, there are air bubbles trapped from the atmosphere of centuries past, tiny time capsules that scientists can study to learn about historical climate conditions. This ancient air is remarkably well preserved. The ice acts as a seal, preventing the air from escaping or being contaminated. Scientists who study ice cores, long cylinders of ice drilled from glaciers and ice sheets, can analyze these air bubbles to determine the composition of the atmosphere at the time the snow fell. They can measure the levels of carbon dioxide, methane, and other gases, and from this, they can reconstruct past climates, understanding how the Earth's atmosphere has changed over millennia. An iceberg, floating in the ocean, is not just a piece of ice. It is a floating archive, a library of atmospheric history, slowly dissolving back into the present. The sound of an iceberg, when you're close enough to hear it, is subtle but distinctive. There's the drip of meltwater, a gentle, irregular patter as water runs off the ice and falls into the sea. There's the creak and groan of the ice itself, the structure adjusting to temperature changes and the stress of its own weight. Sometimes, you'll hear a sharp crack, the sound of a fracture forming, a piece of ice breaking free. And beneath the surface, there are other sounds, the snap and pop of air bubbles being released as the ice melts, a sound that has been described as similar to the crackling of a fire, though much quieter, much more distant. These sounds are part of the iceberg's presence, part of the way it inhabits the space around it. They are not loud, not insistent, but they are there, a reminder that even in stillness, there is activity, there is change, there is a slow unfolding of processes that we can witness if we pay attention. The light around an iceberg can be extraordinary. In the polar regions, the quality of light is different from what most of us experience in our daily lives. The sun, when it is above the horizon, stays low in the sky, casting long shadows and creating a soft, diffused illumination. When this light falls on an iceberg, it brings out the textures and colors of the ice. The white surfaces glow, almost luminous. The blue ice seems to hold the light, radiating it back in a way that makes the blue appear deeper, richer. And when the sun is low, during the golden hours of polar summer or the brief twilight of polar winter, the ice can take on warm hues, pinks and oranges and golds, a startling contrast to the cold blue and white. At night, if the sky is clear and the moon is bright, an iceberg becomes a ghostly presence, a pale shape floating in the darkness. The ice reflects the moonlight, making the iceberg visible even when everything else is lost in shadow. And if you're fortunate enough to be in a place where the aurora borealis or aurora australis is visible, you might see the shimmering curtains of green and red light reflected in the ice, the iceberg becoming a mirror for one of nature's most beautiful phenomena. The wildlife around an iceberg adds another layer to its story. Seabirds often rest on icebergs, using them as platforms in the middle of the ocean. Seals haul out onto the ice, basking in the sun or resting between dives. In the Antarctic, penguins sometimes find their way onto icebergs, standing in groups, their black and white plumage stark against the white ice. These animals are drawn to the icebergs for various reasons. The ice provides a safe resting place, away from predators in the water. It offers a vantage point for spotting food, and in some cases, the cold water around a melting iceberg creates conditions that attract fish and krill, which in turn attract the animals that feed on them. Beneath the surface, the underwater portion of an iceberg can become a kind of oasis. The ice provides a surface for algae and other microorganisms to attach to, and these form the base of a small but vibrant food web. Small fish and invertebrates gather around the iceberg, feeding on the algae and on each other, and larger predators come feed on them. The iceberg, in its slow drift, carries this community with it, a mobile ecosystem traveling through the ocean. The relationship between icebergs and climate is profound. Icebergs are both a product of climate and an influence on it. They form in regions where it is cold enough for snow to accumulate and persist, where glaciers can grow and flow toward the sea. Changes in climate affect the rate at which glaciers flow and the frequency with which icebergs calve. Warmer temperatures can accelerate glacial melting, leading to more icebergs and to larger, more frequent calving events. At the same time, icebergs affect the climate by releasing cold fresh water into the ocean, which can influence ocean currents and heat distribution. The melting of icebergs also contributes to sea level rise, though the contribution from icebergs that have already calved from glaciers is small compared to the melting of ice that is still on land. There is a certain humility in contemplating an iceberg. These are objects shaped by forces that operate on timescales far beyond human life. The ice in an iceberg might have been part of a glacier for 1,000 years, moving so slowly that the distance it traveled in human lifetime will be measured in meters, not kilometers. And yet, here it is, floating in the ocean, visible to us, a tangible connection to deep time, to processes that began long before we were born and will continue long after we're gone. Icebergs remind us that the world is full of slow processes, of changes that unfold gradually, patiently, without regard for our schedules or our sense of urgency. They remind us that stillness is not the same as inactivity, that something can be moving, changing, living, even when it appears perfectly calm. And they offer us, if we're willing to accept it, a different way of experiencing time, a way that is less about counting minutes and more about witnessing the unfolding of natural processes, the drift of ice through water, the slow return of ancient snow to the sea. As you lie here, perhaps beginning to feel the edges of sleep, you can imagine an iceberg drifting through dark water, its white form glowing faintly under the stars. It moves without effort, without thought, carried by currents it cannot resist and does not try to resist. It is going somewhere, though where exactly doesn't matter. The journey itself is the point. The slow, silent drift, the gradual transformation, the patient dissolution. And in imagining this, you might find a kind of permission to let go, to drift yourself, to move into sleep with the same ease, the same lack of resistance, the same trust in the currents that carry you. The ocean currents that carry icebergs are themselves part of something much larger and slower. These currents form great loops and rivers within the sea, driven by differences in temperature and salt content. Where cold water meets warmer water, density shifts occur, and these shifts create motion that can persist for thousands of miles. An iceberg entering such a current becomes a passenger on a journey it did not choose, moving at speeds so gentle that from moment to moment, nothing seems to change at all. The speed of an iceberg's drift varies, but it is almost always measured in fractions. A typical iceberg in the North Atlantic might move at half a knot, which is roughly the pace of a very slow walk. Some move even more slowly, covering only a few hundred meters in a day. Others, caught in faster currents or pushed by steady winds, might travel several kilometers. But even at their swiftest, icebergs remain symbols of patience, their motion nearly imperceptible to anyone standing on their surface. The surface of an iceberg is rarely flat. Wind and sun carve it into ridges, valleys, and strange sculptural forms. Meltwater pools gather in depressions, creating small lakes of the purest freshwater imaginable. These pools are often a startling blue, even brighter than the ice around them, because the water absorbs red light and reflects blue with unusual intensity. On calm days, these pools become mirrors, reflecting the sky and clouds above in perfect stillness. The edges of an iceberg are where change happens most visibly. Here, the ice meets the sea, and the boundary is never stable. Waves lap against the frozen walls, carving notches and alcoves. Sunlight warms the surface, causing slow drips and trickles. Over days and weeks, these small erosions accumulate, and the iceberg's shape transforms. What was once a sharp corner becomes a smooth curve. What was a towering wall becomes a sloping ramp. The iceberg is always becoming something slightly different from what it was. Beneath the waterline, the iceberg's hidden bulk is shaped by forces the surface never feels. Ocean currents flow around and beneath it, wearing away the submerged ice in patterns determined by water temperature and speed. Warmer water erodes faster, creating undercuts, and hollows. Cold currents preserve the ice, allowing it to retain its shape longer. The result is that the submerged portion of an iceberg is often far more complex than the visible part, a landscape of caves and overhangs and channels that no human eye will ever see. The color of icebergs shifts with the light. Under the bright midday sun of the polar summer, an iceberg gleams white and blue, almost too bright to look at directly. In the softer light of dawn or dusk, it takes on warmer tones, pale gold, soft pink, lavender. On overcast days, the ice appears gray and subdued, blending with the sea and sky. And in the dim twilight of the polar night, an iceberg becomes a ghostly presence, barely distinguishable from the darkness around it, a shadow among shadows. Some icebergs carry within them layers of sediment and rock, picked up during their time as part of a glacier. As the glacier moved over land, it scraped the bedrock beneath, gathering particles of stone and soil. When the glacier reached the sea and calved, these particles became embedded in the ice. As the iceberg melts, the sediment is released, drifting down through the water column to settle on the ocean floor. In this way, icebergs transport pieces of one landscape to another, carrying the mountains to the sea. The journey of an iceberg is also a journey through temperature zones. Most icebergs are born in the coldest regions of the planet, where air and water temperatures rarely rise above freezing. As they drift away from their birthplace, they enter progressively warmer waters. This transition is gradual, almost imperceptible at first, but it determines the iceberg's fate. The warmer the water, the faster the melting. An iceberg that drifts into tropical waters will not survive long, dissolving into the sea within days or weeks. The wind plays a quiet but persistent role in an iceberg's drift. Even though most of the iceberg is underwater, the portion above the surface catches the wind like a sail. A strong, steady wind can push an iceberg in a direction that differs from the ocean current below. When wind and current oppose each other, the iceberg moves in a compromised direction, a vector sum of the two forces. When they align, the iceberg travels faster, gliding through the water with a grace that belies its immense mass. Icebergs are not entirely silent, though their sounds are subtle and infrequent. Occasionally, as the ice shifts and adjusts to changing temperatures and pressures, it emits soft creaks and groans. These sounds are the iceberg speaking, expressing the stresses within its structure. Meltwater trickling across the surface creates a gentle murmur, a sound like a distant stream. And when a piece of ice breaks away and falls into the sea, there is a splash, brief, and soon absorbed by the vastness of the ocean. The lifespan of an iceberg is measured in months or years, depending on its size and the conditions it encounters. A small iceberg in warm waters might last only a few weeks. A large tabular iceberg in the cold Antarctic waters can survive for a decade or more, drifting slowly around the continent, gradually diminishing, but never in a hurry to disappear. Each iceberg's life is unique, shaped by the currents it encounters, the temperatures it endures, and the winds that push it along. The salt content of the ocean affects how an iceberg melts. Salt water has a lower freezing point than fresh water, which means that even when the ocean is very cold, it can still melt ice. The interface between the freshwater ice and the saltwater sea is a place of constant exchange. Fresh meltwater, being less dense than salt water, rises to the surface, creating a thin layer of cold, fresh water around the iceberg. This layer can temporarily insulate the ice, slowing the melting process slightly, but cannot stop it. Icebergs also influence the water around them. As they melt, they release not only fresh water, but also nutrients that were trapped in the ice. These nutrients can fertilize the surrounding ocean, supporting the growth of phytoplankton, the microscopic plants that form the base of the marine food web. In this way, a melting iceberg becomes a source of life, a floating oasis in the open ocean. Small fish gather near icebergs to feed on the plankton, and larger predators follow, creating temporary ecosystems that exist only as long as the iceberg lasts. The shape of an iceberg affects how it interacts with waves. A tall, narrow iceberg will rock and sway in the swell, its center of gravity high and unstable. A low, broad iceberg is more stable, riding the waves with less motion. The most stable icebergs are the tabular ones, with their flat tops and wide bases. These icebergs can travel through rough seas with barely a tremor, their immense mass dampening the effect of the waves. But even the most stable iceberg is not immune to the ocean's power. Over time, wave action erodes the base, and the iceberg's stability can change, sometimes suddenly. Some icebergs become grounded, their keels touching the ocean floor in shallow waters. When this happens, the iceberg stops drifting and remains in place, anchored by its own weight. Grounded icebergs can stay in one location for months or even years, slowly melting in place. They become landmarks, visible from shore, and sometimes they affect local currents and tides. Eventually, as the iceberg melts and its keel becomes lighter, it may lift off the bottom and resume its drift, or it may melt away entirely while still grounded. The Antarctic produces the largest icebergs on Earth, some of them so vast that they are given names and tracked by satellite. These giant tabular icebergs can be hundreds of kilometers long, with flat tops that resemble floating plains of ice. They break away from the ice shelves that fringe the Antarctic continent, massive sheets of ice that extend out over the ocean. When a section of an ice shelf breaks free, it becomes an iceberg, drifting away from the continent on the circumpolar current that flows endlessly around Antarctica. The circumpolar current is the longest and most powerful ocean current on the planet, a river of water that circles Antarctica without interruption. Icebergs caught in this current can travel all the way around the continent, a journey of thousands of kilometers that can take years to complete. Along the way, they gradually melt, shrinking in size but maintaining their tabular shape for much of their journey. Some of these icebergs eventually drift northward, escaping the circumpolar current and entering warmer waters, where their melting accelerates. The Arctic produces smaller icebergs than the Antarctic, but they are no less remarkable. Most Arctic icebergs come from the glaciers of Greenland, which flow down from the island's ice sheet to the sea. These glaciers are among the most active in the world, calving frequently and producing a steady stream of icebergs. The icebergs drift southward along the coast of Greenland, carried by the Labrador Current, which flows down the eastern coast of Canada. Some of these icebergs reach as far south as Newfoundland, where they become hazards to shipping. The Labrador Current is cold, flowing south from the Arctic, and it carries icebergs into regions where they are not expected. Ships traveling the North Atlantic must be vigilant, especially in spring and early summer when iceberg numbers are highest. The International Ice Patrol, established after the sinking of the Titanic, monitors iceberg locations and provides warnings to mariners. Using aircraft, satellites, and computer models, the patrol tracks icebergs and predicts their drift, helping to keep shipping lanes safe. Icebergs have been a hazard to navigation for as long as humans have sailed polar waters. In fog or darkness, an iceberg can appear suddenly, giving little time to react. The visible portion of the iceberg is only a small part of the danger. The submerged portion extends far beyond what can be seen, and a ship can strike the underwater ice even when it seems to have passed the visible part safely. Modern radar and sonar help detect icebergs, but in rough seas or poor visibility, they remain a threat. The temperature of the air around an iceberg is often noticeably cooler than the surrounding environment. An iceberg acts as a floating refrigerator, cooling the air that comes into contact with it. On a calm day, this cold air can create a layer of fog around the iceberg, a ghostly veil that obscures its outline. Sailors have learned to recognize this fog as a sign of ice nearby, a warning to proceed with caution. The fog itself is formed when warm, moist air meets the cold air around the iceberg and condenses into tiny water droplets. The melting of an iceberg is not uniform. The top surface melts faster in direct sunlight, while the shaded sides melt more slowly. The waterline, where the ice meets the sea, is a zone of intense melting, carved by waves and warmed by the relatively warmer water. This uneven melting can cause the iceberg to become unstable. If too much ice melts from one side, the center of gravity shifts, and the iceberg may roll over, seeking a new equilibrium. These rollovers are sudden and dramatic, though they happen without warning and are rarely witnessed. Icebergs can also split apart as they melt. Cracks that were invisible or insignificant when the iceberg was whole can widen as the ice warms and weakens. Water seeps into these cracks, and if it refreezes, it expands, forcing the crack wider. Eventually, the crack may propagate all the way through the iceberg, and it splits into two or more pieces. Each piece then becomes its own iceberg, drifting independently, each with its own shape and destiny. The density of ice is about 90% that of seawater, which is why icebergs float with roughly 10% of their volume above water. But this ratio can vary slightly depending on the ice's porosity and the salinity of the water. Ice that contains many air bubbles is less dense and floats higher. Ice that is compressed and dense floats lower. The salter the water, the denser it is, and the higher an iceberg will float in it. These are small variations, but they affect how much of the iceberg is visible and how it interacts with waves and currents. The age of the ice in an iceberg can be thousands of years old. Glaciers form from snow that falls year after year, each layer compressing the layers beneath it. Over centuries and millennia, the snow transforms into ice, trapping within it tiny bubbles of ancient air. When a glacier calves and an iceberg is born, it carries this ancient ice out to sea. Scientists sometimes study icebergs to learn about past climates, analyzing the trapped air and the isotopic composition of the ice to reconstruct temperatures and atmospheric conditions from long ago. The sound of an iceberg melting is a quiet symphony of drips, trickles, and occasional cracks. On a warm day, meltwater flows across the surface in small streams, gathering in channels and cascading over edges in miniature waterfalls. The sound is gentle, almost musical, a counterpoint to the vast silence of the polar ocean. Occasionally, a piece of ice will crack and fall, creating a sharp sound that echoes briefly before being swallowed by the sea. These sounds are the iceberg's slow dissolution, a process so gradual that it seems almost peaceful. Icebergs are habitats, temporary but vital, for certain species. Seabirds rest on their surfaces, finding a safe platform away from predators. Seals haul out onto icebergs to rest or give birth, using the ice as a refuge from the water. Polar bears in the Arctic sometimes ride icebergs, though this is more common with sea ice than with icebergs themselves. These animals are opportunistic, using whatever resources the environment provides, and an iceberg, for a time, can be a home. The color variations within an iceberg tell stories of its history. White ice is full of air bubbles, formed from snow that was not fully compressed. Blue ice is denser, with fewer bubbles, and it has been under pressure for a longer time. Sometimes, icebergs contain layers of darker ice, stained by sediment or organic material. These layers are visible as bands or streaks, and they reveal the different conditions the glacier experienced as it formed. Reading an iceberg is like reading the pages of a book, each layer a chapter in a story that spans centuries. The speed at which an iceberg melts depends on many factors: water temperature, air temperature, sunlight, wind, and wave action. In the coldest waters, melting is slow, and an iceberg can persist for years. In warmer waters, melting accelerates, and an iceberg can disappear in weeks. The transition is not always smooth. An iceberg can drift through zones of different temperatures, melting quickly in one area and slowly in another. This variability makes predicting the lifespan of any individual iceberg difficult. Icebergs contribute to the ocean's freshwater budget. As they melt, they release fresh water into the sea, slightly lowering the salinity of the surrounding water. In regions where many icebergs are melting, this input of fresh water can be significant, affecting local ocean currents and ecosystems. The fresh water is cold, and it tends to stay near the surface, creating stratification in the water column. This stratification can influence the mixing of nutrients and the distribution of marine life. The movement of icebergs is influenced by the Coriolis effect, a consequence of the Earth's rotation. In the northern hemisphere, moving objects are deflected to the right, and in the southern hemisphere, to the left. This deflection affects ocean currents, which in turn affect iceberg drift. An iceberg drifting in the North Atlantic will tend to curve to the right as it moves south, while an iceberg in the Southern Ocean will curve to the left. The effect is subtle, but over long distances, it shapes the paths that icebergs follow. Some icebergs contain pockets of liquid water within them, trapped in voids and channels within the ice. This water is incredibly pure, having been isolated from the ocean and filtered by the ice itself. These pockets can be quite large, sometimes forming caverns within the iceberg. As the iceberg melts, these caverns can collapse, causing sudden shifts in the iceberg's shape and stability. The existence of these internal water pockets is one reason why icebergs can be unpredictable, changing their behavior without visible cause. The transparency of ice varies. Some ice is so clear that you can see deep into it, as if looking through a window. Other ice is opaque, clouded by air bubbles and impurities. The clearest ice is the densest, formed under the greatest pressure, and it has a jewel-like quality, refracting light in beautiful ways. When sunlight passes through clear ice, it can create rainbows and halos, brief moments of color in the white and blue landscape. These optical effects are fleeting, visible only when the light is just right, but they add to the iceberg's quiet beauty. Icebergs are monuments to patience. They form over centuries, drift for months or years, and melt slowly back into the sea. There is no urgency in their existence, no rush to reach a destination. They move when the currents move them, melt when the warmth touches them, and split when the stresses within them become too great. They are entirely passive, responding to the forces around them without resistance or intent. In this way, they're the opposite of human life, which is so often filled with haste and purpose. The silence around an iceberg is profound, far from land, far from the noise of human activity. The polar ocean is one of the quietest places on Earth. The only sounds are natural: the whisper of wind, the gentle slap of waves, the distant call of a seabird. An iceberg drifting in this silence becomes part of it, a presence that adds to the stillness rather than disturbing it. To be near an iceberg is to experience a kind of peace that is rare in the modern world, a reminder that not everything needs to be loud or fast or urgent. The study of icebergs is a branch of glaciology, the science of ice. Researchers track icebergs using satellites, which can detect them even in the remotest parts of the ocean. They measure their size, speed, and trajectory, building models to predict how icebergs will behave under different conditions. This research is important for understanding ocean currents, climate change, and the dynamics of ice sheets. But beyond the science, there is something humbling about studying icebergs, about trying to understand objects so vast and slow and indifferent to human concerns. Icebergs have inspired artists, writers, and explorers for generations. Their stark beauty, their immense scale, and their serene drift through the ocean have a kind of majesty that is hard to put into words. Painters have tried to capture their colors and forms, photographers have documented their shapes, and poets have written about their solitude. But no representation can fully convey what it is like to stand before an iceberg, to feel its cold breath, to hear the soft sounds of its melting, to witness its slow, silent journey across the sea. The iceberg is a reminder of the planet's power and patience. It is born from snow that fell centuries ago, compressed into ice by the weight of more snow, pushed slowly to the sea by the inexorable flow of the glacier. It breaks free in a moment of violence, then spends the rest of its existence in slow, peaceful dissolution. It asks nothing, needs nothing, and gives nothing except its presence. And in that presence, there is something calming, something that invites us to slow down, to breathe, to simply be. The polar regions where icebergs are born are among the most remote and inhospitable places on Earth. They are cold, dark for much of the year, and scoured by fierce winds. Yet they are also places of profound beauty and tranquility. The ice and snow create landscapes of almost surreal purity, where the only colors are white, blue, and the occasional gray of rock or the dark of open water. In these landscapes, icebergs are not anomalies, but natural features, as much a part of the environment as the glaciers that birth them. The relationship between icebergs and the ocean is one of constant exchange. The iceberg gives fresh water and nutrients. The ocean gives motion and warmth. Neither dominates. Both participate in a balance that has existed for millions of years. This balance is part of the larger system of the Earth's climate, a system so complex and interconnected that changing one part affects all the others. Icebergs are both products of this system and contributors to it, small players in a vast, slow dance. The drift of an iceberg is a kind of meditation on time. Human life is measured in decades, and we experience time as something that moves quickly, filled with events and changes. But an iceberg experiences time differently. Its journey is measured in seasons and years, and the changes it undergoes are so gradual that they are almost invisible from one moment to the next. To watch an iceberg is to be reminded that not all things happen quickly, that some processes unfold at their own pace, indifferent to our desire for speed. The cold of an iceberg is absolute. Even on a relatively warm day, the ice remains frozen, its temperature well below the freezing point of water. This cold is ancient, a remnant of winters long past, preserved in the ice and carried forward through time. When you touch an iceberg, you are touching something that has not been warm in centuries, perhaps millennia. It is a strange and humbling sensation, a connection to a past that is otherwise unreachable. Icebergs are also symbols of hidden depth. The phrase, tip of the iceberg, has entered common language to mean that what is visible is only a small part of a larger whole. This is literally true for icebergs, where the vast majority of their mass is hidden beneath the water. But it is also metaphorically true for many things in life, where what we see on the surface conceals complexities and depths that are not immediately apparent. The iceberg, in this way, is a teacher, reminding us to look beyond the obvious, to consider what lies beneath. The end of an iceberg's journey is not dramatic. There is no final explosion, no sudden collapse. Instead, the iceberg simply melts away, growing smaller and smaller until it is nothing more than a patch of floating ice. And then even that is gone, absorbed back into the ocean from which it came. The water that was once ice becomes indistinguishable from the water around it, carrying with it the memory of mountains and glaciers and the long, slow journey across the sea. And in that quiet ending, there's a kind of completeness, a return to the beginning, a cycle fulfilled. The journey through iceberg science continues, unfolding layer by layer, fact by fact, each one a small doorway into the quiet mechanics of frozen water adrift in open ocean. There is something deeply restful in knowing that these processes have repeated for millennia, that the ice you imagine now follows the same invisible rules that guided bergs centuries ago, long before anyone thought to study them. Consider the way an iceberg interacts with the atmosphere above it. The air immediately surrounding a large iceberg is often several degrees cooler than the air just a few hundred meters away. This creates a microclimate, a pocket of chilled air that hovers over the ice like a soft blanket. On calm days, this cool air can be so stable that it forms a thin layer of fog, clinging to the surface of the berg, obscuring its edges. The fog is not dramatic. It simply rests there, a veil of moisture suspended between ice and sky. This cooling effect extends beyond the iceberg itself. Ships passing within a kilometer of a large berg often report a noticeable drop in temperature, even when the ice is not yet visible. Sailors have long used this phenomenon as an early warning system, a gentle signal that ice lies ahead. The air itself becomes a messenger, carrying the presence of the iceberg across the water long before the eye can confirm it. And the iceberg, for its part, remains indifferent to this exchange. It does not warm the air or push it away. It simply exists, and the air responds, cooling in proximity, rising slightly as it warms again, creating slow convection currents that swirl almost imperceptibly above the ice. These currents are too gentle to disturb the surface of the sea, but they are there, a silent conversation between frozen water and open sky. Beneath the surface, the iceberg continues its slow dialogue with the ocean. The meltwater it releases is not only fresh and cold, it is also filled with microscopic particles of rock and sediment, remnants of the glacier's long journey across land. These particles, ground fine by the immense pressure of moving ice, are carried into the surrounding water as the berg melts. They settle slowly, drifting downward through the water column, sometimes taking days to reach the seafloor. This sediment, though invisible to the naked eye, plays a quiet role in the ocean's chemistry. It can carry trace minerals, iron among them, which are essential nutrients for phytoplankton. In some parts of the ocean, particularly in the Southern Ocean around Antarctica, iron is a limiting nutrient, meaning that phytoplankton growth is constrained by its availability. When an iceberg releases iron-rich sediment, it can spark small blooms of phytoplankton in its wake, tiny green clouds of life that spread across the surface, visible from space. These blooms are not large or sudden. They unfold gradually, over days and weeks, as the phytoplankton absorbs sunlight and multiply. The bloom may extend for several kilometers behind the drifting iceberg, a subtle trail of productivity in an otherwise barren stretch of ocean. The iceberg itself moves on, unaware of the life it has kindled, continuing its slow journey toward warmer water. The shape of an iceberg also influences how it melts, and this in turn affects the water around it. A tall, narrow berg, often called a pinnacle, melts differently than a flat, tabular berg. The pinnacle has more surface area exposed to air relative to its volume, which means it loses mass more quickly through surface melting and sublimation. The tabular berg, by contrast, melts more slowly at the surface, but may experience more rapid melting along its submerged edges, where warmer water circulates. As a pinnacle melts, it often becomes top-heavy, its base eroding faster than its peak. This imbalance can cause the berg to tip or roll, a process that happens slowly, almost gently, over the course of hours. The roll is not violent. The iceberg simply shifts, finding a new equilibrium, settling into a more stable configuration. When it does, it releases a soft wave that radiates outward, a ripple of displaced water that travels across the surface and fades into the distance. Tabular bergs, with their flat tops and steep sides, are less prone to rolling but more likely to fracture. As the submerged shelf melts unevenly, cracks can form along the length of the berg, spreading slowly through the ice. These cracks may remain dormant for weeks, invisible except as faint lines on the surface. Then, one day, the berg splits, calving a smaller piece that drifts away on its own trajectory. The separation is quiet, marked only by the soft sound of ice parting and the gentle splash as the new fragment settles into the water. The color of meltwater itself is worth pausing over. When a large iceberg melts, the water it releases is not entirely clear. It carries with it tiny bubbles of ancient air, particles of sediment, and sometimes a faint milky hue from suspended glacial flour, fine silt ground by the glacier over centuries. This meltwater spreads across the surface of the ocean, mixing slowly with the salt water around it. For a time, the boundary between fresh and salt is visible, a subtle line where the water changes texture, where light refracts differently. This boundary, called a halocline, is a place of transition. It is not sharp or sudden, but gradual, a zone where salinity increases step by step as you move away from the iceberg. The halocline can extend for hundreds of meters, a soft gradient that marine life often navigates instinctively. Some fish prefer the fresher water near the berg, where the temperature is cooler and oxygen is more abundant. Others stay in the saltier water beyond, where the density is greater and the currents more predictable. The iceberg, drifting through this layered ocean, is itself a layered structure. Its ice is not uniform. Near the surface, the ice may be relatively young, formed from snow that fell only a few hundred years ago. Deeper within the berg, the ice is older, compressed under the weight of subsequent snowfalls, its bubbles smaller and fewer. At the very core of some icebergs, the ice can be thousands of years old, a frozen archive of ancient climates, holding within it traces of atmospheric gases, volcanic ash, and even pollen from plants that grew in distant lands. Scientists have studied ice cores taken from glaciers, and these cores reveal a history written in layers. Each year of snowfall leaves a distinct mark, a thin band that can be read like a page in a book. By analyzing these layers, researchers can reconstruct past temperatures, atmospheric composition, even the intensity of solar radiation. The iceberg carries this history with it. Though it is slowly erased as the ice melts, the ancient layers dissolving into the sea, their information lost. Yet while it drifts, the iceberg is a messenger from the past. The air bubbles trapped within its ice are samples of the atmosphere as it was centuries ago, sealed away and preserved. When the ice melts, these bubbles are released, and the ancient air mixes with the modern atmosphere, a tiny reunion of past and present. The release is silent, invisible, a breath from history dissolving into the wind. The iceberg's interaction with sunlight is another source of quiet wonder. During the polar summer, when the sun barely sets, an iceberg is bathed in light for nearly 24 hours a day. This constant illumination affects how the ice melts. The sun warms the surface, causing it to soften and become slightly sticky. Meltwater pools form in shallow depressions on the top of the berg, collecting in small ponds that reflect the sky. These ponds can be startlingly blue, their color intensified by the depth of the water and the purity of the ice beneath. As the summer progresses, these melt ponds can grow, spreading across the surface of the berg. Some become large enough to support their own small ecosystems. Algae begin to grow in the water, tinting it green, and tiny invertebrates may arrive, carried by the wind or by seabirds. These ponds are temporary, existing only as long as the ice remains solid enough to hold them. Eventually, the water finds a crack or a weak point and drains through the berg, carving channels through the ice, creating a network of tunnels and passages that weaken the structure from within. The sound of water moving through an iceberg is delicate, a soft trickling that echoes faintly within the ice. It is not loud enough to hear from a distance, but if you were standing on the berg itself, you might catch it. A gentle murmur, the sound of the berg slowly dismantling itself, one drop at a time. In the polar winter, when the sun disappears for months, the iceberg's experience changes entirely. The surface no longer melts. Instead, it refreezes, becoming harder and more brittle. Snow falls on the berg, accumulating in layers, adding weight and insulation. The iceberg becomes quieter, more dormant, drifting through the dark, its process is slowed almost to a halt. The ocean around it may begin to freeze, forming sea ice that locks the berg in place, holding it motionless until the spring thaw. During this time, the iceberg is not entirely inactive. Even in the cold, the ice continues to creep, to shift microscopically under its own weight. The internal structure adjusts, crystals realigning, stress fractures forming and healing. These changes are imperceptible from the outside, but they are happening, a slow internal dance that continues regardless of the season. When the sun returns, the sea ice melts, and the iceberg is freed once more. It resumes its drift, often in a new direction, pushed by currents that have shifted during the winter months. The berg may be smaller now, worn down by the slow grinding of sea ice against its sides, but is still intact, still moving, still following the invisible paths laid out by the ocean. The lifespan of an iceberg, from calving to complete dissolution, can vary enormously. A small berg in warm water may last only a few weeks. A massive tabular iceberg in the cold waters of the Antarctic can survive for years, even decades. One iceberg, tracked by satellite, drifted for over 18 years, traveling thousands of kilometers before finally melting away. During that time, it circled the Antarctic continent, caught in the circumpolar current, a slow, endless loop that carried it through some of the most remote waters on Earth. The longevity of an iceberg depends on many factors: its size, its shape, the temperature of the water, the strength of the currents, the amount of sunlight it receives. But perhaps most important is the depth of the ocean through which it travels. Icebergs that drift into deep water, where the currents are stable and the temperature remains consistently cold, can survive much longer than those that venture into shallow coastal areas, where warmer water and turbulent conditions accelerate melting. There is something profoundly calming in the idea that an iceberg can drift for decades, moving so slowly that its progress is almost invisible, yet covering distances that span continents. It is a reminder that not all journeys are rapid, that some things move at a pace so gradual it defies human perception, yet they are moving nonetheless, carried by forces that never rest. The iceberg does not resist its fate. It does not struggle against the warmth of the water or the pull of the current. It simply drifts, accepting each moment as it comes, dissolving slowly, particle by particle, until nothing remains but the memory of its passage. A slight change in salinity, a brief bloom of plankton, a ripple on the surface that fades into stillness. And in this acceptance, there is a kind of peace. The iceberg teaches, without words, that dissolution is not failure. It is simply transformation, a return to the ocean from which it was once drawn, a completion of cycle that has no true beginning or end. The ocean, for its part, absorbs the iceberg without fanfare. The meltwater mixes, the temperature adjusts, the currents continue. The ocean is vast enough to accommodate countless icebergs, each one a small contribution to the whole, each one a temporary visitor that arrives, lingers, and departs, leaving only the faintest trace. As the iceberg melts, it also releases sound, not the sharp crack of calving or the rumble of a roll, but something quieter, a soft hissing, almost like a whisper, as trapped air escapes from the ice. This sound is most noticeable when a piece of iceberg ice is placed in water. The ice, formed under pressure, contains thousands of tiny bubbles, each one a pocket of compressed air. As the ice melts, these bubbles are freed, and they rise to the surface, releasing their air in a gentle fizz. This phenomenon is sometimes called Bergy seltzer, a whimsical name for a process that is both simple and beautiful. The sound is soothing, a quiet effervescence that can continue for several minutes as the ice slowly dissolves. It is the sound of ancient air returning to the atmosphere, a reunion that happens without ceremony, noticed only by those who pause to listen. The iceberg, even as it diminishes, continues to interact with its environment in subtle ways. Its presence alters the local temperature, the salinity, the light, the sound. It provides a surface for birds to rest upon, a source of fresh water for seals, a landmark for navigators. It is a participant in the ecosystem, not merely a passive object drifting through it. Birds, in particular, are drawn to icebergs. Gulls, petrels, and skuas often perch on the flat surfaces of tabular bergs, using them as resting platforms during long flights over open water. The ice is stable, cool, and free from predators, a safe haven in an otherwise featureless expanse. From the air, a large iceberg dotted with resting birds can resemble a small island, a temporary refuge that will vanish within weeks or months. Seals, too, find icebergs useful. They haul out onto the ice to rest, to give birth, to escape from predators in the water. A seal on an iceberg is relatively safe from orcas and leopard seals, which cannot easily climb onto the slippery surface. The iceberg becomes a nursery, a sanctuary, a place where life can pause and gather strength before returning to the sea. The relationship between icebergs and marine mammals is ancient and instinctive. Seals do not learn to use icebergs. They simply do, guided by behaviors passed down through countless generations. The iceberg, in turn, offers no resistance. It is simply there, solid and cool, indifferent to the life that clings to it. Even the smallest icebergs, fragments no larger than a car, play a role. They drift through the water, melting slowly, contributing their fresh water and nutrients to the surrounding ocean. They are too small to be tracked by satellite, too insignificant to be named or studied. Yet they are part of the same process, the same slow dissolution that defines all icebergs. They are the quiet majority, the uncounted masses that dissolve in anonymity, their contributions invisible but real. The beauty of an iceberg is not only in its appearance, but in its impermanence. It is beautiful precisely because it is temporary, because it will not last, because it is in the process of becoming something else. This transience is not sad. It is simply the nature of ice and water, the inevitable result of thermodynamics, the quiet unfolding of entropy. And yet, while it exists, the iceberg is fully itself. It is solid, real, present. It reflects light, casts shadows, makes sound, moves through space. It is not waiting to melt. It is simply being moment by moment, until the moment it is no longer ice but water, no longer separate but merged, no longer visible but dispersed. The icebergs drift, is also influenced by the Coriolis effect, the same force that shapes weather patterns and ocean currents. In the northern hemisphere, the Coriolis effect causes moving objects to veer to the right. In the southern hemisphere, they veer to the left. An iceberg drifting through the ocean is subject to this force, though its effect is subtle, a gentle nudge that gradually alters the berg's trajectory over days and weeks. This means that an iceberg does not travel in a straight line, even if the current is steady. It curves ever so slightly, tracing a path that spirals slowly across the ocean. The curve is too gradual to see in real time, but over the course of weeks, the deviation becomes apparent. The iceberg that seemed to be heading due north is now angling northeast, guided by forces it cannot perceive, following a path it did not choose. The Coriolis effect is strongest at the poles and weakest at the equator. This is one reason why icebergs rarely cross the equator. By the time they drift into tropical latitudes, they have long since melted. But the effect is always present, always shaping the movement of the ice, an invisible hand guiding the berg through the water. The ocean floor beneath a drifting iceberg is often far below, thousands of meters down in some cases. The iceberg, floating at the surface, has no contact with the bottom, no awareness of the abyssal plains and deep trenches over which it passes. Yet the depth of the water influences the currents that carry the berg, and thus indirectly shapes its journey. Deep water currents are more stable, less affected by wind and surface conditions. An iceberg drifting over deep water tends to move more steadily, more predictably, than one in shallow coastal areas where currents are complex and variable. In some regions, icebergs do scrape the bottom. This happens in shallow coastal waters, where the berg's keel, the submerged portion, extends deep enough to touch the seafloor. When this occurs, the iceberg can gouge the bottom, carving long furrows in the sediment. These furrows, called iceberg scours, can be hundreds of meters long and several meters deep. They are visible in sonar surveys of the ocean floor, long parallel lines that mark the passage of icebergs decades or even centuries ago. The process of scouring is slow and steady. The iceberg does not plow through the sediment like a ship through water. Instead, it drags, its keel pressing into the soft mud or sand, displacing it gradually as the berg drifts. The sediment is pushed aside, piled up along the edges of the furrow, creating low ridges that flank the scour. Over time, these ridges settle and erode, but the furrow itself can remain visible for years, a scar on the seafloor that tells the story of an iceberg's passage. The icebergs that create these scours are usually large and deep-keeled, with submerged portions extending 50 meters or more below the surface. They are the giants of the iceberg world, the massive tabular bergs that calve from ice shelves and drift through polar waters for years. Their scours are found primarily in the waters around Antarctica and Greenland, in regions where the seafloor is relatively shallow and the icebergs are plentiful. The presence of these scours affects the seafloor ecosystem. The furrows disrupt the sediment, burying some organisms and exposing others. They create new habitats, depressions where water can pool, ridges where currents are altered. Over time, these disturbed areas are recolonized by marine life, and the scour becomes part of the landscape, a feature that shapes the distribution of species and the flow of nutrients. The iceberg, having left its mark, drifts on, unaware of the change it has wrought. It continues its journey, moving into deeper water, where its keel no longer touches the bottom, where the ocean floor recedes into darkness far below. The temperature of the iceberg itself is not uniform. The surface, exposed to air and sunlight, is warmer than the interior, though warmer is a relative term. The surface might be near 0 degrees Celsius, while the core remains at -10 or colder. This temperature gradient creates stress within the ice, as the warmer outer layers expand slightly while the colder core remains rigid. Over time, this stress can cause cracks to form, fractures that spread slowly through the ice, weakening the structure. These internal fractures are invisible from the outside, hidden within the white mass of the berg. But they are there, growing, connecting, forming networks of weakness that will eventually cause the berg to break apart. The fracturing is a slow process, driven by temperature changes, by the weight of the ice, by the constant flexing and bending as the berg rides the waves. It is not sudden or dramatic. It is simply the ice responding to the forces acting upon it, adjusting, yielding, breaking where it must. When a fracture finally reaches the surface, the iceberg calves, shedding a piece of itself. The fragment drifts away, and the parent berg, now lighter and smaller, rises slightly in the water, its equilibrium restored. The cycle continues, each calving event a small step in the berg's gradual dissolution, each fragment a new iceberg beginning its own brief journey. The iceberg's color, too, changes as it melts. Fresh ice, newly calved, is often bright white, its surface covered with a layer of snow or frost. As the berg drifts and melts, this surface layer washes away, revealing the denser ice beneath. This ice can be pale blue, almost translucent, especially where the surface is smooth and wet. The blue deepens in areas where the ice is thick and the light must travel far through it, absorbing the warmer colors and reflecting only the cool tones. In some places, the ice is streaked with darker bands, layers of sediment or volcanic ash that were incorporated into the glacier as it moved across land. These bands create patterns, stripes that run through the berg, marking the history of its formation. The patterns are subtle, often visible only when the light is right, but they are there, a record written in ice, slowly dissolving as the berg melts. The iceberg, in its final days, becomes a shadow of its former self. What was once a towering mass is now a low, rounded hump, barely rising above the waterline. The surface is pocked and uneven, sculpted by sun and waves into a landscape of hollows and ridges. The ice is thin, fragile, ready to break at the slightest disturbance. And then, one day it is gone. The last fragment melts, the final bubble of air escapes, and the iceberg ceases to exist. The water where it floated is slightly cooler, slightly fresher, but these differences fade quickly, absorbed by the vastness of the ocean. Within hours, there is no trace, no sign that the iceberg was ever there. But the ocean remembers, in its way. The meltwater has mixed, the nutrients have dispersed, the plankton have bloomed and multiplied. The iceberg's passage has altered the ocean, however slightly, and those alterations ripple outward, affecting currents, temperatures, ecosystems. The iceberg is gone, but its influence remains, woven into the fabric of the sea, invisible but enduring. And somewhere, far to the south or north, another iceberg is calving, beginning its own journey, drifting into the same currents, following the same paths, dissolving slowly under the same sun. The cycle continues, unbroken, unhurried, a rhythm as old as the ice itself. The iceberg's journey continues in ways both visible and hidden, each moment a quiet testament to forces older than human memory. As it drifts through waters that shift with the seasons, the berg becomes a participant in cycles that connect atmosphere to ocean, surface to depth, present to past. The relationship between ice and water remains one of constant negotiation, a dialogue conducted in the language of temperature and pressure, salinity and current. When an iceberg encounters warmer water masses, the melting accelerates along specific zones. The waterline becomes a place of active transformation, where ice meets liquid in a boundary that shifts hourly. The warmth doesn't distribute evenly. It concentrates where currents flow strongest, where the sun's angle penetrates deepest. This creates asymmetrical melting patterns that alter the berg's balance. What was stable yesterday may tip tomorrow as the center of mass migrates with each kilogram of ice lost to the sea. The tipping events themselves unfold with surprising gentleness most of the time. An iceberg doesn't always roll violently. Sometimes it simply settles into a new orientation over the course of hours, responding to the gradual shift in its weight distribution. The water around it swirls gently as the berg rotates, creating temporary eddies that dissipate within minutes. These slow rotations reveal surfaces that haven't seen sunlight in months or years, exposing ice that has remained submerged since the berg first calved from its glacier. Each newly exposed surface carries its own character. Ice that has been underwater often appears smoother, polished by the constant flow of water across its face. It may be darker, stained by minerals or organic matter that settled onto it during its time below. When this ice emerges into air and light, it begins to change immediately. The sun warms it, the wind dries it, and within hours it develops the same rough texture as the rest of the berg's aerial surfaces. The transformation happens quietly, without announcement, another small revision in the iceberg's ongoing story. The sound an iceberg makes vary with its size and condition. Smaller bergs, especially those heavily fractured, produce frequent small cracks and pops as internal stresses release. These sounds carry through both air and water, though they're often too faint to hear unless you're very close. Larger, more solid bergs remain quieter, their mass absorbing and dampening the small movements that would create noise in a smaller structure. The silence of a massive tabular iceberg can be profound, broken only by the occasional distant rumble as a piece separates from its edge. Beneath the surface, the iceberg's underwater portion creates a unique acoustic environment. Sound waves traveling through the ocean bend around the ice, creating zones of acoustic shadow where certain frequencies cannot penetrate. Marine mammals sometimes use these shadows, swimming through areas where their vocalizations are partially shielded from distant listeners. The iceberg becomes an unintentional acoustic barrier, altering the soundscape of the surrounding ocean in ways that shift as the berg melts and changes shape. The meltwater plume, rising from an iceberg's base, doesn't flow uniformly. It spirals and pulses, responding to the irregular melting rates across different parts of the underwater ice. Where the ice is colder or more dense, melting proceeds slowly. Where cracks or cavities allow warmer water to penetrate deeper into the ice structure, melting accelerates. The result is a meltwater plume with internal structure, streams within streams, each carrying slightly different temperatures and mineral contents toward the surface. This complexity in the meltwater creates microenvironments for plankton. Certain species of phytoplankton thrive in the transitional zones where fresh meltwater mixes with salt water at specific ratios. These zones shift constantly as the plume's structure changes, creating a dynamic habitat that exists only temporarily. The plankton populations respond quickly, blooming and dispersing within days as conditions evolve. The iceberg thus generates not just one habitat, but a succession of habitats, each lasting only briefly before conditions shift again. The minerals released by melting ice include not just iron, but trace amounts of manganese, zinc, copper, and other elements essential to marine life. These elements were captured as the glacier formed, incorporated into the ice as snow fell onto the glacier's surface over centuries. Some minerals came from dust blown onto the glacier from distant continents, particles that traveled thousands of kilometers through the atmosphere before settling onto the ice. Now, as the iceberg melts, these minerals return to circulation, completing journeys that began decades or centuries ago. The concentration of these trace elements in iceberg meltwater is typically very low, measured in parts per billion. Yet, even at these concentrations, They can influence biological productivity in waters where such elements are naturally scarce. The Southern Ocean, which surrounds Antarctica, is often iron-limited. Sunlight and nutrients are abundant, but the lack of iron constrains phytoplankton growth. An iceberg releasing even small amounts of iron can trigger blooms that extend far beyond the meltwater plume itself, as currents distribute the iron across larger areas. These phytoplankton blooms can be detected from satellites, appearing as patches of greener water against the darker ocean. Scientists studying these blooms have traced some back to individual large icebergs, watching as the bloom develops in the berg's wake and then spreads downwind and downcurrent. The bloom may persist for weeks, supporting zooplankton populations that in turn feed fish and larger animals. A single iceberg can thus influence ocean productivity across hundreds of square kilometers, its ecological footprint extending far beyond its physical presence. The iceberg's drift speed varies not just with current and wind, but with its own changing shape. As melting alters the berg's underwater profile, the way water flows around it changes. A berg that develops a deep keel extending far below the surface will be more influenced by deep currents than by surface winds. A berg that melts into a flatter shape will respond more readily to wind, its increased surface area relative to its underwater mass, making it more susceptible to being pushed by air currents. Some icebergs develop complex underwater shapes as they melt. Differential melting can create overhangs, cavities, and protruding ridges beneath the waterline. These features alter the berg's hydrodynamics, creating drag in some directions and reducing it in others. An iceberg with a large underwater overhang might drift sideways more easily than forward, moving in directions that seem unrelated to the apparent wind and current directions. The berg's motion becomes a puzzle, solvable only by understanding its hidden underwater geometry. The temperature of the ice itself changes as the berg drifts into warmer waters. The surface ice warms quickly, reaching temperatures close to the melting point within hours of entering warmer air. But the interior of a large iceberg warms much more slowly. Heat conducts through ice at a finite rate, and for a berg with a radius of hundreds of meters, the core may remain at temperatures well below freezing even as the outer layers melt away. This creates a temperature gradient within the ice, with the coldest ice at the center and progressively warmer ice toward the edges. This internal temperature structure influences how the berg fractures. Cold ice is more brittle, fracturing cleanly under stress. Warmer ice, closer to the melting point, is more plastic, deforming rather than breaking under the same stress. When a fracture propagates through an iceberg, it may travel easily through the cold interior, but slow or stop when it reaches the warmer outer layers. This can result in partial fractures that don't fully separate pieces from the main berg, creating attached fragments that hang precariously until further melting or wave action completes the separation. The color variations visible on an iceberg surface tell stories of its history. Blue ice indicates dense, old ice with few air bubbles, ice that has been compressed under its own weight for many years. White ice contains more air bubbles, reflecting light in all directions and appearing opaque. Bands of white and blue reveal layers that formed under different conditions, perhaps years with heavier snowfall alternating with years of less accumulation, each leaving its signature in the ice. These bands can be traced across the berg's surface, mapping out the glacier's history in frozen stratigraphy. Some icebergs carry visible layers of sediment, dark lines running through the ice where the glacier scraped across bedrock and incorporated rock dust into its structure. These sediment layers are especially common in icebergs that calve from glaciers with complex flow patterns, where ice from the glacier's base, ice that has been in contact with bedrock, gets folded up into higher layers through the glacier's internal deformation. When such an iceberg melts, the sediment is released, sinking through the water column to settle on the seafloor far from its original location. The process of iceberg decay is not uniform across all bergs. Some melt primarily from below, thinning gradually until they become unstable and break apart. Others melt more rapidly at the waterline, developing a notch that deepens until the overhanging ice can no longer support its own weight and collapses. Still, others fracture internally, their structure weakening from within until the berg suddenly disintegrates into thousands of smaller pieces. The specific path each berg follows toward its dissolution depends on its size, shape, internal structure, and the environmental conditions it encounters. Tabular icebergs, with their flat tops and steep sides, often develop melt ponds on their upper surfaces during warmer months. These ponds form when surface ice melts faster than the meltwater can drain away, creating shallow lakes of liquid water on top of the ice. The water in these ponds is slightly warmer than the surrounding ice, and it absorbs more sunlight than white ice would, accelerating the melting beneath the pond. Over time, these ponds can deepen, sometimes melting all the way through the berg to create channels or holes that connect the top surface to the ocean below. When a melt pond drains through the berg, the sudden flow of water can carve smooth channels through the ice. These channels, once formed, continue to evolve as meltwater flows through them in subsequent warm periods. Some become permanent features of the berg structure, tunnels that remain open even as the surrounding ice continues to melt. Swimming through such a tunnel, if one could do so safely, would reveal walls of blue ice, polished smooth by flowing water, illuminated by light filtering through the ice from above. The light within an iceberg is a phenomenon of subtle beauty. Sunlight penetrating the ice scatters and reflects internally, creating a diffuse glow that can make the ice seem to emit light from within. The color of this internal light depends on the ice's density and purity. Very clear, bubble-free ice transmits light with minimal scattering, allowing deeper penetration and creating a deep blue glow. Ice with more air bubbles scatters light more strongly, reducing penetration depth and shifting the color toward lighter blue or white. Cracks and fractures within the ice create patterns of light and shadow. Where the ice is fractured, light can penetrate along the cracked surfaces, illuminating internal structures that would otherwise remain dark. These illuminated fractures create intricate patterns visible from outside the berg, lines of brighter blue cutting through the darker ice. The patterns change as the sun moves across the sky, the angle of illumination revealing different aspects of the berg's internal structure throughout the day. The interaction between icebergs and sea ice creates interesting dynamics in polar regions. When an iceberg drifts through a field of sea ice, it can push the thinner ice aside, creating a wake through the ice field. The berg's momentum, carried by deep currents, allows it to plow through ice that would stop a ship. Behind the berg, the sea ice may close in again, or the wake may remain open, creating a lead, a channel of open water that other animals can use for breathing and travel. Some icebergs become frozen into sea ice during winter, their drift halted until the sea ice breaks up in spring. While frozen in place, the berg becomes part of the ice field structure, a thick anchor point around which thinner sea ice flexes and moves. The berg's mass extends far below the sea ice, unaffected by the seasonal freezing and thawing that governs the thinner ice around it. When spring arrives and the sea ice begins to break up, the berg is released, resuming its drift as if awakening from a long pause. The age of the ice in an iceberg can span centuries. Ice from the interior of a large Antarctic ice shelf may have formed 500 or 1,000 years ago, snow that fell when human civilization looked very different than it does today. This ice contains air bubbles that trapped atmospheric gases from those earlier times, preserving samples of the ancient atmosphere. When the iceberg melts and these bubbles are released, They return gases to the atmosphere that have been isolated from the air-ocean system for centuries, though in quantities too small to measurably affect atmospheric composition. Scientists occasionally sample icebergs to study the ice's chemical composition and the gases trapped within it. These samples provide information about past climate conditions, atmospheric composition, and even volcanic eruptions that deposited ash onto the glacier's surface centuries ago. Each layer of ice is a time capsule, and an iceberg is a drifting archive, carrying information about the past into the present until melting releases it back to the ocean. The sound of an iceberg calving from a glacier is one of nature's most powerful acoustic events. The initial crack can be heard kilometers away, a sharp report like thunder. This is followed by the roar of ice breaking and falling, a sound that can last for minutes as thousands or millions of tons of ice collapse into the ocean. The impact generates waves that radiate outward, and the sound travels through both air and water, announcing the birth of a new iceberg to the surrounding environment. But once the iceberg has calved and begun its drift, the loudness fades. The berg settles into its new existence as a separate entity, no longer part of the glacier's constrained flow. The sounds it makes now are quieter, the occasional crack of internal stress, the gentle splash of ice falling from its edges, the soft hiss of air bubbles escaping as submerged ice melts. The transition from the violence of calving to the quietness of drift is complete within hours, and the berg becomes a silent traveler. The wake an iceberg creates as it moves through the water is often minimal, especially if the berg is moving slowly. The water flows smoothly around the berg's underwater surfaces, creating gentle currents rather than turbulent eddies. This smooth flow means the berg moves efficiently through the water, with relatively little energy lost to turbulence. The ocean accepts the berg's presence without resistance, allowing it to drift with minimal disturbance to the surrounding water. Occasionally, an iceberg will drift into shallow water, where its deep keel approaches or touches the seafloor. When this happens, the berg may slow dramatically or even stop, grounded on the bottom. A grounded iceberg can remain in place for months or years, held fast by its contact with the seafloor. During this time, it continues to melt, gradually reducing its draft until it floats free again. The area of seafloor where the berg was grounded often shows clear evidence of the contact: scraped sediment, displaced rocks, and sometimes deep gouges where the berg dragged across the bottom before coming to rest. Grounded icebergs create localized upwelling as currents deflect around them. Water forced to flow up and over the berg brings nutrients from deeper layers toward the surface, potentially enhancing biological productivity in the immediate area. The berg becomes a temporary feature of the local oceanography, altering flow patterns and creating habitat complexity that wouldn't exist in its absence. When the berg finally floats free and drifts away, the oceanographic conditions return to their previous state, though the marks on the seafloor remain as evidence of the berg's presence. The relationship between icebergs and climate is complex and reciprocal. Climate influences where and when icebergs form, how quickly they melt, and where they drift. But icebergs also influence climate, though more subtly. The meltwater they release affects ocean salinity, which influences water density and ocean circulation. The cooling effect of melting ice extracts heat from the surrounding water, slightly lowering ocean temperatures in areas where icebergs are abundant. And the biological productivity stimulated by iceberg-released nutrients affects the ocean's capacity to absorb carbon dioxide from the atmosphere. These effects are small on a global scale, but can be significant regionally. In areas where many large icebergs drift and melt, the cumulative effect of their meltwater can create measurable changes in ocean properties. The water becomes fresher, colder, and potentially more productive. These changes propagate through the marine ecosystem, influencing species distributions and food web dynamics. The iceberg, in its slow dissolution, becomes an agent of environmental change, its influence extending through physical, chemical, and biological pathways. The lifespan of an iceberg varies enormously. Small bergs calved from Greenlandic glaciers might melt completely within weeks of entering the warmer waters of the North Atlantic. Giant tabular bergs from Antarctica can drift for years, traveling thousands of kilometers before finally melting away. The largest Antarctic icebergs ever observed have persisted for a decade or more, their immense volume providing enough ice to withstand years of melting. These long-lived bergs become familiar features of the Southern Ocean, tracked by satellites, and sometimes given names by the researchers who monitor their progress. The naming of large icebergs follows a systematic approach. When a significant iceberg is detected, it receives a designation based on the Antarctic quadrant where it originated and a sequential number. This naming system allows scientists to track individual bergs over time, documenting their drift paths, size changes, and eventual breakup. Some named icebergs have become famous in scientific circles, their journeys documented in detail, and their influence on ocean conditions studied extensively. The breakup of a large iceberg into smaller pieces doesn't happen all at once. Instead, it's a gradual process of fragmentation. A large berg might shed smaller pieces from its edges over months, each fragment becoming an independent iceberg with its own drift path. Eventually, the original berg may split into several large pieces, each continuing to drift and melt separately. The final stage of breakup often comes when the berg has melted enough to become structurally weak, at which point it may suddenly disintegrate into a field of small fragments that melt away within days. This progression from intact berg to fragment field represents the final chapter of the iceberg's existence. The fragments, too small to be individually tracked, disperse across the ocean surface. Each piece melts rapidly, its small size meaning that heat can penetrate to its core within hours. Within days, the fragments have vanished, their substance returned entirely to the ocean. Where once a massive iceberg drifted, now only slightly cooler, slightly fresher water remains, mixing quickly with the surrounding ocean until even this trace disappears. The memory of the iceberg persists in other ways. The sediment it released settles on the seafloor, a layer of fine particles that may be detected in seafloor cores decades or centuries later. The nutrients it provided may have supported a plankton bloom that fed zooplankton, which fed fish, which fed seals or seabirds. The iceberg's substance thus incorporated into living tissue and carried far from where the berg melted. The cooling effect of its meltwater may have influenced local ocean temperatures in ways that affected currents or weather patterns, effects that cascade through the climate system in ways difficult to trace but nonetheless real. The study of icebergs has evolved significantly with advances in technology. Satellites can now detect and track icebergs across entire ocean basins, providing data on their size, location, and drift speed. Autonomous instruments deployed on or near icebergs measure temperature, salinity, and other properties, transmitting data that helps scientists understand the melting process and the berg's influence on its environment. Ships equipped with specialized sensors can map the underwater shape of icebergs, revealing the hidden geometry that determines how the berg drifts and melts. Despite these technological advances, much about icebergs remains incompletely understood. The internal structure of a large iceberg, its fractures, density variations, and temperature gradients, is difficult to measure without drilling into the ice, a challenging undertaking on a drifting, unstable platform. The exact mechanisms that trigger sudden calving events or iceberg rollovers are still being investigated, with researchers combining observations, theoretical models, and laboratory experiments to understand the physics involved. The aesthetic appeal of icebergs has made them subjects of art and photography for as long as humans have encountered them. Early explorers sketched icebergs in their journals, trying to capture the strange beauty of these ice mountains floating in the sea. Photographers have documented icebergs in every possible light: dawn, noon, dusk, and night, revealing how the ice transforms visually with changing illumination. The images show icebergs as sculptures, each one unique, shaped by forces that create forms no human artist could plan or predict. The emotional response many people have to images of icebergs is complex. There's a sense of awe at their size and beauty, but also sometimes a melancholy recognition of their impermanence. An iceberg is a transient thing, beautiful precisely because it is temporary. It exists in a state of constant change, never the same from one day to the next, always in the process of becoming something else. This impermanence resonates with human experiences of change and loss, giving icebergs a symbolic weight beyond their physical presence. In literature and film, icebergs often serve as symbols of hidden depth, the familiar image of most of the berg being underwater, representing the idea that what's visible is only a small part of a larger reality. This metaphor has been used so often that it's become a cliché, yet it persists because it captures something true about icebergs and about human perception. We see the surface, the visible part, but the greater mass remains hidden, influencing events in ways we might not immediately recognize. The reality of icebergs is both simpler and more complex than the metaphor suggests. Yes, most of the iceberg is underwater, a straightforward consequence of ice density and buoyancy. But the underwater portion isn't mysterious or hidden in any intentional sense. It's simply below the waterline, invisible from above, but not unknowable. Modern sonar and other technologies can map it in detail. The iceberg doesn't hide its underwater mass. We simply can't see it from our usual vantage point of the surface. Yet there's a deeper truth in the metaphor. The iceberg's influence extends far beyond its visible boundaries. The meltwater plume, the altered currents, the nutrients released, the organisms supported. These effects ripple outward in ways that are indeed hidden, not because they're underwater, but because they're diffuse, distributed across space and time in ways that make them difficult to perceive directly. The iceberg's full impact on its environment is far larger than the ice itself, an influence that extends in dimensions beyond the merely physical. The iceberg, in its patient drift through polar seas, embodies a particular kind of existence, one defined by slow change, by the gradual working of natural forces, by participation in cycles that span years and centuries. It doesn't resist its dissolution. It simply melts, each moment of its existence, both an ending and a continuation. The ice that melts today becomes ocean water, which may evaporate and fall as snow on a glacier, which may eventually become part of another iceberg in a future century. The cycle continues, indifferent to individual bergs, each one a temporary expression of water's journey through the Earth system. The iceberg continues its drift through waters that grow warmer with each passing day. The journey that began in cold polar darkness now extends into regions where sunlight penetrates more deeply, where water temperatures rise by fractions of a degree, where the ocean's embrace becomes gentler but more insistent. The berg responds to these changes not with resistance, but with quiet acceptance, its form adapting to circumstances beyond its control, its substance gradually returning to the sea from which it ultimately came. The patterns of melting become more pronounced as the iceberg moves into warmer latitudes. What began as subtle surface dissolution now accelerates into more visible transformation. Channels deepen into grooves. Grooves widen into valleys. Valleys expand into caverns that penetrate the berg's interior, allowing seawater to circulate through passages that reshape the ice from within. The iceberg becomes a sculpture of water carved by water, its form determined by the interplay of temperature, current, and time. The surface of the berg develops textures that change throughout the day. Morning sun creates a slightly softened layer that refreezes during cooler nights, forming a thin crust that cracks and shifts with the berg's movement. This daily cycle of melting and refreezing creates patterns that resemble tree rings, each layer marking a day in the iceberg's diminishing life. The patterns accumulate, overlap, and eventually dissolve, leaving no permanent record except in the memory of water itself. The iceberg's color shifts as its journey progresses. The deep blue that characterized its densest ice begins to fade as air pockets expand and multiply. The white of surface ice becomes more prevalent as internal structures collapse and reform. Occasional bands of sediment, once locked deep within the berg, now appear at the surface as melting reveals layers that were buried for millennia. Each color tells a story of origin, of compression, of time measured in snowfall and pressure and patient accumulation. The berg's interaction with sunlight creates moments of unexpected beauty. When the sun reaches certain angles, light penetrates the ice and illuminates internal features that are invisible at other times. Fractures glow with soft blue radiance. Air bubbles scatter light into tiny stars suspended within solid water. The entire berg can seem to hold light within itself, glowing from within like a lantern made of frozen time. These moments pass as the sun moves, as the berg rotates, as circumstances shift and change. The sounds of melting become more frequent as the iceberg enters warmer waters. The quiet dripping that accompanied earlier stages now intensifies into a constant percussion of water returning to water. Streams flow across the berg's surface, carving temporary channels that change course with each shift in the ice's orientation. Small waterfalls cascade from elevated sections, their sound mixing with the deeper groans of internal stress and the sharp cracks of fracturing ice. The iceberg becomes an orchestra of dissolution, each sound marking a moment of transformation. The berg's center of gravity continues to shift as melting proceeds unevenly. The underwater portion dissolves faster than the visible summit, creating imbalances that accumulate over days and weeks. The iceberg compensates by tilting slightly, adjusting its orientation to maintain equilibrium. These adjustments happen slowly, almost imperceptibly, but they represent the berg's constant negotiation with physics, its ongoing attempt to find stability in the midst of continuous change. Occasionally, the accumulated imbalance becomes too great for gradual adjustment. The iceberg tips suddenly, rotating in the water to find a new orientation of stability. These rolling events happen without warning, driven by internal mathematics of mass and buoyancy. The berg might rotate 90 degrees, presenting a previously submerged face to the sky, or it might flip completely, inverting itself so that what was once the deepest underwater section now forms the visible peak. Each rotation reveals ice that has been hidden, exposing surfaces carved by underwater currents, smoothed by contact with the sea. The newly exposed surfaces carry evidence of their time beneath the waves. They are smoother than the weathered upper sections, polished by water flow and the gentle abrasion of suspended particles. They may be darker, stained by minerals or organic matter from the ocean depths. They often contain embedded rocks or sediment that the iceberg carried from its glacial source, now revealed like secrets brought to light. These surfaces begin immediately to weather in their new environment, subjected to sun and air and the different dynamics of exposure. The iceberg's wake changes character as the berg shrinks. The disturbance it creates in the water becomes less pronounced. The trail of cold meltwater becomes narrower. The influence on surrounding temperature gradients diminishes. What was once a significant presence in the ocean surface layer becomes gradually less distinct, its boundaries with the surrounding sea becoming softer, less defined. The iceberg begins to blend with its environment, its identity as a separate entity slowly fading. The populations of organisms associated with the berg shift as conditions change. Species that thrived in the coldest meltwater near the berg's surface find their habitat shrinking, compressed into smaller zones as the overall temperature differential decreases. Some species migrate away, following temperature gradients to other ice sources. Others adapt to the changing conditions, adjusting their behavior and distribution. A few species increase in abundance as the berg's diminishing size creates conditions that favor their particular requirements. The phytoplankton blooms that flourished in the iceberg's iron-rich meltwater begin to fade as the supply of nutrients changes. The bloom's peak passes, and the microscopic plants that multiplied so rapidly now face depletion of resources and increased grazing pressure from zooplankton populations that have grown in response to the abundance. The bloom collapses gradually, its organic matter sinking through the water column, carrying carbon and nutrients to deeper layers. This transfer represents the berg's ongoing contribution to ocean chemistry, its influence extending far beyond its physical presence. The iceberg passes through regions where other bergs have traveled before. The ocean here carries subtle signatures of previous ice, slight variations in salinity and temperature that mark the passage of frozen travelers. These signatures are faint, detectable only through precise measurement, but they represent a kind of conversation between icebergs separated by time. Each berg adds its voice to this ongoing exchange, contributing its particular chemistry to waters that remember, however briefly, every piece of ice that has dissolved within them. The berg encounters patches of sea ice as it drifts through certain regions. These are thin sheets of frozen seawater, fundamentally different from the ancient glacier ice of the berg itself. The sea ice is younger, measured in months rather than millennia. It is saltier, less dense, more fragile. The iceberg moves through these patches like an elder among children, its massive bulk unimpeded by the thin sheets that crack and part around its passage. The contrast highlights the berg's unique nature, its origin in terrestrial snowfall rather than ocean freezing. The temperature within the iceberg's core remains remarkably cold, even as the surface melts. The interior ice, insulated by outer layers and possessing tremendous thermal mass, resists warming. Measurements taken from the center of large icebergs have recorded temperatures far below freezing, preserving conditions from the ice's formation even as the berg drifts through relatively warm waters. This temperature gradient creates internal stress, as cold interior ice contracts while warmer surface layers expand, contributing to the fracturing and calving that gradually reduces the berg size. The iceberg's meltwater contains dissolved gases that were trapped when the ice formed. As the ice melts, these gases are released into the ocean and atmosphere. The composition of these gases reflects atmospheric conditions from the time of the ice's formation, potentially centuries or millennia ago. Scientists have studied these gas releases as windows into past climates, reading the chemical signatures like messages from distant times. Each bubble that rises from melting ice carries information, a tiny archive of ancient air. The patterns of cracks on the iceberg's surface create maps of stress and strain. Where the ice has been compressed, cracks run in certain directions. Where it has been stretched or twisted, the fracture patterns differ. Where temperature gradients have been steepest, the density of cracks increases. Reading these patterns requires understanding the physics of ice, the history of the berg's formation, and the forces it has experienced during its journey. The surface becomes a text written in fractures, telling stories to those who know the language. The iceberg occasionally encounters marine mammals that use it as a resting platform. Seals haul out onto accessible ice shelves, finding temporary refuge from predators and the constant demands of swimming. They rest on the ice's solid surface, their breathing slowing, their bodies recovering from the exertion of hunting and traveling. The iceberg provides this service without intention, its existence creating opportunities for life to pause and rest. The seals leave eventually, slipping back into the water, but their brief presence adds another layer to the berg's ecological significance. Birds sometimes land on icebergs during long ocean flights. The ice offers a resting place far from any shore, a solid surface in the midst of endless water. The birds might stay for minutes or hours, preening their feathers, scanning for food in the waters around the berg, conserving energy before continuing their journeys. The iceberg becomes a way station, a point of reference in the featureless expanse of ocean. The birds leave no lasting mark, but their visits connect the berg to migration patterns that span continents. The iceberg's journey sometimes brings it near shipping lanes, where vessels pass at regular intervals. The ships give the berg wide berth, their navigation systems tracking its position, their crews alert to the danger posed by ice. The iceberg drifts unaware of these precautions, its movement governed by currents and wind rather than any awareness of human activity. The ships pass, their wakes spreading outward, and the iceberg continues its drift, unchanged by the proximity of human technology and purpose. The water around the berg sometimes becomes unusually calm, creating conditions of extraordinary clarity. In these moments, the underwater portion of the iceberg becomes visible from the surface, its submerged bulk apparent through the transparent water. The view reveals the berg's true scale, the massive underwater architecture that supports the visible peak. The smooth surfaces, the deep crevasses, the gradual taper toward the bottom, all become briefly visible before wind or current disturbs the water's clarity and the underwater realm returns to concealment. The iceberg's drift sometimes carries it into regions where bioluminescent organisms are abundant. At night, the water around the berg glows with soft blue-green light as microscopic creatures respond to disturbance with chemical luminescence. The berg's movement through these waters creates trails of light, its wake glowing with the collective radiance of countless tiny lives. The effect is ethereal, transforming the dark ocean into a field of living light, with the iceberg at its center like a dark island surrounded by glowing sea. The moon's phases affect the iceberg's appearance and the behavior of life around it. During full moons, the berg's white ice glows with reflected light, becoming a beacon visible for miles across dark water. The increased illumination affects the behavior of marine organisms, altering feeding patterns and predator-prey interactions in the waters surrounding the ice. During new moons, the berg disappears into darkness, its presence marked only by sound and the slight difference in water temperature. The cycle repeats monthly, creating rhythms that overlay the berg's longer journey toward dissolution. The iceberg carries within its ice tiny particles of dust and pollen from its place of origin. These particles traveled through the atmosphere before settling on the glacier's surface, becoming incorporated into snow that eventually compressed into ice. As the berg melts, these particles are released into ocean waters far from their source, completing journeys that began in distant ecosystems. The particles settle to the seafloor or are consumed by filter-feeding organisms, becoming part of the ocean's sedimentary record or biological cycles. The berg's surface develops pools of meltwater during warm periods. These pools form in depressions on the ice's upper surface, collecting water that cannot immediately drain away. The pools are often strikingly blue, their color intensified by the ice beneath them. They warm in the sunlight, reaching temperatures several degrees above freezing, creating microenvironments distinct from both the ice and the surrounding ocean. Some pools eventually drain through cracks that reach the berg's interior, sending streams of relatively warm water into the ice's cold heart. The iceberg's interaction with weather patterns creates localized effects. The cold air above the ice can trigger fog formation when it meets warmer, moisture-laden air from surrounding waters. The fog clings to the berg, obscuring its form, creating an atmosphere of mystery and concealment. Within the fog, visibility drops to meters, and the berg becomes a presence felt rather than seen, its existence marked by the sound of dripping water and the subtle chill in the air. The berg sometimes passes through waters rich in jellyfish, their translucent bodies drifting in currents like living ghosts. The jellyfish are indifferent to the iceberg's presence, their simple nervous systems registering only light, chemical signals, and physical contact. They pulse through the water around the berg, their movement creating gentle currents, their tentacles trailing behind them. The iceberg and the jellyfish share the water without interaction, each following patterns determined by different forces, different timescales, different purposes. The iceberg's final weeks are characterized by accelerating transformation. The berg has shrunk to a fraction of its original size, its mass diminished by months of continuous melting. The processes that operated slowly at first now proceed rapidly, the smaller size offering less resistance to warming, less thermal inertia to slow the inevitable conclusion. The berg becomes more fragile, more vulnerable to the forces that have been working on it throughout its journey. The remaining ice develops a delicate, almost lacy structure as melting creates intricate patterns of holes and thin walls. The berg resembles a sculpture created by an artist obsessed with light and transparency, each surface carved to maximize the passage of illumination, each remaining section reduced to minimal thickness. The structure is beautiful but unstable, maintained only briefly before collapsing under its own weight or the pressure of waves. The iceberg's final days might see it break into several smaller pieces, each continuing independently for a time. These fragments drift apart, following slightly different currents, experiencing slightly different conditions. Each piece carries within it the same ancient ice, the same compressed snow, the same history, but each will complete its dissolution separately, in its own time, in its own location. The single iceberg becomes multiple endings, scattered across kilometers of ocean. Alternatively, the berg might remain largely intact until the very end, shrinking steadily but maintaining its basic form. In this scenario, the iceberg gradually diminishes until it reaches a size where it can no longer maintain stability. A final tipping event might break it apart, or it might simply melt away, growing smaller and smaller until the last piece of ice dissolves into the sea, leaving nothing but a slight anomaly in the water's temperature and chemistry. The final moments of an iceberg's existence are rarely observed. The process usually occurs far from human witnesses, in remote waters where the only observers are the organisms that have accompanied the berg or the satellites that track large ice masses from orbit. The iceberg disappears without ceremony, its substance returning to liquid form, its journey complete, its story ending in the quiet mixing of fresh water with salt water, cold with warm, ice with ocean. The water that was once ice spreads into the surrounding sea, mixing and dispersing. Within hours, the temperature anomaly fades. Within days, the salinity difference becomes undetectable. Within weeks, the water that composed the iceberg has been incorporated into the ocean's vast circulation, indistinguishable from any other water molecule, its origin as glacier ice erased by the thoroughness of mixing. The iceberg's physical presence ends completely, leaving only indirect evidence of its passage. Yet the iceberg's influence persists in subtle ways. The nutrients it released have fueled biological productivity that continues in its absence. The sediments it deposited rest on the seafloor, becoming part of the geological record. The organisms that fed in its meltwater have grown and reproduced, carrying forward the energy and matter the berg provided. The iceberg's effects ripple forward in time, extending beyond the berg's physical existence. The space the iceberg occupied is now empty water, indistinguishable from the surrounding ocean. Currents flow through the area without obstruction. Waves pass unimpeded. The temperature and salinity match the regional averages. Nothing visible marks the location where the berg spent its final days. The ocean has absorbed the iceberg completely, incorporating its mass and energy into the larger system, erasing the boundary between ice and water. This disappearance is not an ending, but a transformation. The water molecules that form the iceberg continue to exist, continue to move, continue to participate in the ocean's endless cycling. They will evaporate into the atmosphere, form clouds, fall as rain or snow, flow through rivers, freeze and thaw, rise and sink. Some molecules might eventually return to polar regions, become incorporated into glaciers, and begin the journey again. The cycle has no true beginning or end, only continuous transformation. The iceberg story is one among countless similar stories. At any given moment, thousands of icebergs drift through polar and subpolar waters, each at a different stage of its journey, each responding to unique combinations of current, temperature, and wind. Some are freshly calved, massive and angular, still carrying the shape of the glacier from which they broke. Others are ancient and weathered, reduced to fragments, days or hours from complete dissolution. Together, they represent a continuous process, a flow of ice from land to sea, a transfer of frozen fresh water into the ocean's salt water. The contemplation of icebergs offers a particular kind of peace. Their movement is slow enough to seem almost motionless, yet constant enough to remind us that change is always occurring. Their size is impressive but not threatening. Their presence powerful but not aggressive. They exist in some of the most remote and quiet places on Earth, far from human noise and activity, drifting through waters that remain largely as they have been for millennia. There is something deeply calming about the patience of icebergs. They do not rush toward their dissolution. They do not resist the forces that gradually reduce them. They simply exist, moment by moment, responding to conditions, adapting to circumstances, following the paths that currents and winds create. Their journey is determined by forces beyond their control, yet they move with a kind of dignity, a quiet acceptance of process and change. The iceberg asks nothing of the observer. It does not perform or display. It simply is, existing in its own time, following its own trajectory. To watch an iceberg, even in imagination, is to participate in a kind of meditation on time and change, on the relationship between solid and liquid, on the patient working of natural processes. The iceberg becomes a teacher of sorts, demonstrating through its existence lessons about impermanence, about the beauty of gradual transformation, about the peace that comes from accepting rather than resisting change. In the quiet of evening, when the day's activities have ended and the mind begins to slow, the image of an iceberg drifting through dark waters offers a focus for relaxation. The berg moves so slowly that its motion is barely perceptible. The water around it is calm, disturbed only by the gentle rise and fall of swells. The sky above might be dark with stars, or gray with clouds, or lit by the soft colors of aurora. The iceberg continues its drift, patient and unhurried, a presence of stillness in the midst of the ocean's vastness. The sounds around the iceberg are minimal. The quiet lap of water against ice, the occasional crack of internal stress, the soft drip of meltwater, the distant calls of seabirds, the whisper of wind across the berg's surface. These sounds create a soundscape of profound quietness, where silence is not empty, but filled with subtle, peaceful noise. The sounds do not demand attention, but offer themselves to listening, creating an atmosphere of calm. The temperature of the air near the iceberg is cool, but not uncomfortable in imagination. There is a freshness to it, a clarity that comes from the proximity of ice and the cleanness of polar air. The coolness is refreshing rather than harsh, a gentle reminder of the berg's nature, its origin in cold places, its composition of frozen water. To imagine standing near an iceberg is to imagine breathing air that is pure and clear, untouched by pollution or warmth. The light around the iceberg changes with the time of day and season. In polar summer, the sun might circle the horizon without setting, creating light that lasts for months. The iceberg will be continuously visible, its form changing subtly as the sun's angle shifts but never disappearing into darkness. In polar winter, the opposite occurs, and the berg drifts through months of twilight and darkness, visible only when moon or stars provide illumination, or when aurora paint the sky with shifting curtains of light. The iceberg exists in a realm that feels separate from human time and human concerns. It moves through waters that are rarely traveled, past horizons that few people see, following currents that have flowed for millennia. Its existence is governed by physics and chemistry, by the properties of water and ice, by the grand circulation of ocean and atmosphere. Human activity affects these systems in the aggregate, but the individual iceberg drifts largely untouched by human hands, following patterns that predate human civilization. To think about icebergs is to connect with something larger than individual human experience. It is to consider processes that operate on scales of time and space that dwarf human lifetimes and human landscapes. An iceberg might contain ice that formed before recorded history began. It might drift for years through waters that have never known human presence. It will eventually melt and disappear, its substance returning to cycles that will continue long after human civilization has transformed or ended. Yet despite this vast scale, there is something intimate about the iceberg story. It is, after all, just water. The same substance that fills our glasses, falls as rain, flows in our rivers, forms our clouds. The iceberg is made of the same molecules that surround us constantly, that make up most of our bodies, that are essential to all life we know. The iceberg's grandeur and its familiarity coexist, making it both extraordinary and ordinary, both distant and close. The iceberg's silence is perhaps its most profound quality. It makes no sound that travels far. It announces itself through presence rather than noise. Its movement creates no roar or rumble, just the quiet displacement of water, the gentle disturbance of currents. Even its breaking and melting, while occasionally dramatic, produce sounds that fade quickly into the ocean's ambient noise. The iceberg is a monument to quietness, to the possibility of significance without loudness, of power without aggression. In a world that often feels too loud, too fast, too demanding, the iceberg offers an alternative. It suggests that movement can be slow and still meaningful, that change can be gradual and still profound, that existence can be quiet and still significant. The iceberg does not need to justify its presence or prove its worth. It simply is drifting and melting, following the patient logic of physics and chemistry, participating in cycles that are larger than any single entity. As we consider the iceberg's journey from glacier to ocean, from solid to liquid, from ice to water, we might find in it a metaphor for our own transformations. We too change gradually, shaped by forces both internal and external. We too move through time, following paths we only partially control. We too will eventually return our substance to the larger cycles from which we emerged. The iceberg's peaceful acceptance of its dissolution might offer us a model for approaching our own changes and endings with less resistance and more grace. The iceberg reminds us that endings are also transformations. The ice does not cease to exist when it melts. It changes form. The molecules continue, participating in new processes, taking new shapes, serving new purposes. What appears to be an ending is also a continuation, a transition from one state to another. The iceberg story does not conclude with its melting, but continues in the water molecules that spread through the ocean, rise into the atmosphere, fall again as precipitation, and begin new journeys. There is comfort in this continuity. Nothing is truly lost, only transformed. The iceberg's substance persists even after the berg itself has disappeared. The water remains, cycling through the Earth's systems, connecting ocean to atmosphere to land and back again. The iceberg was always part of this cycle, and its melting is simply a return to a different phase of the same endless process. As your thoughts slow and your breathing deepens, the image of the iceberg can remain with you. A white shape drifting through dark water, a presence of coolness and calm, a reminder that change can be slow and peaceful, that silence can be profound, that transformation is natural and continuous. The iceberg asks nothing of you, but offers much, a focus for a wandering mind, a symbol of patience, a connection to processes that are ancient and ongoing. If you're still awake, still listening, there are more stories to explore, more natural processes to consider, more quiet corners of science to visit. The world is full of phenomena that can soothe and fascinate, that can help the mind release its grip on daily concerns and drift into the peaceful spaces between waking and sleep. These stories are here whenever you need them, patient as icebergs, waiting to guide you toward rest. But if sleep is approaching, if your awareness is already beginning to blur and fade, that is exactly right. The iceberg will continue its drift without you. The ocean will continue its circulation. The cycles will continue their turning. Everything will continue as it should, and you can release your attention, allowing yourself to float into sleep as the iceberg floats through water, supported and carried, peaceful and unhurried. The iceberg moves through the night, through waters that are dark and calm. Its journey continues, patient and inevitable, a slow transformation that needs no witnesses, no documentation, no understanding. It simply is existing in its own time, following its own path, a presence of ice and silence in the vast, quiet ocean. And that is enough. That has always been enough. That will always be enough. Rest now, if you are ready. The icebergs will continue their drift. The ocean will continue its patient work. The cycles will turn, and you can let go, allowing sleep to come as naturally as ice melts into water, as quietly as an iceberg moves through the dark sea, as peacefully as snow falls on a distant glacier, beginning again the long, slow journey from mountain to ocean, from solid to liquid, from waking to sleep.